Okay, so we want to look at the approach of resonance, which I kind of messed, not kind of messed, I mean, I did a lot of it right, then I couldn't get the function to do what I know it's going to do, okay? So, just using the notation of the book, we've got this equation, okay? This is, if this was 0, that's just plain old simple harmonic motion, okay? This isn't 0, this is a driving function, okay? Now, generally, there'll be a coefficient in front of this. But if there is, no big deal. You just put a coefficient in front of what you get for the particular solution. Okay? So you can work that out. What we want to see is how what we think ought to happen happens. You got a kid on a swing, and you start using an electromagnetic pulse to give him just a little push every so often. And you're going to give him that little push kind of close to the natural frequency of the swing. I just said this a minute ago, but for the sake of the camera, you know. So the pushes, just little pushes, but they're close to the natural frequency of the swing, so the kid will swing out just a little bit, he'll come back, and he'll come here, and right at about the right point, he'll get another push, which means he'll swing out a little further. He'll pretty much have twice the energy he did from the first push. But you're a little bit off, so it's not quite twice the energy, okay? And then every time you push them, you're just off by a little more. So eventually, you're going to get totally out of phase, and you're going to be pushing him when he's coming at you, and you're going to start dissipating his energy. So his amplitude's going to increase for a while, then it's going to decrease. It's going to become down to pretty much 0, and it's all going to start over again. So you have this sine function. It starts low and then gets bigger and gets bigger to get it, you know, hit the graph of its position versus time, and then it's going to get smaller. So you got a graph that kind of does this and then this with, you know, sine wave in between within this envelope here. Okay? And you've seen pictures of that. It's in your book. So that's what's going on. Now, how does this differential equation give us this? Okay? Well, we solve the equation. Homogeneous solution's this. So whatever our initial conditions are, the homogeneous solution is going to be what it is. Okay? Now, I'm starting with the simplest possible initial conditions that the kid's stationary at equilibrium, which means your homogeneous solution is going to be 0. You know, you're not giving the kid any energy to start, any velocity to start with, and he's at equilibrium. He's not going anywhere unless something happens, right? Well, here's your pulsing push. Omega naught's the natural frequency of this pendulum. Omega 1 is the frequency, the angular frequency of your push, right?
So how do we get that homogeneous solution?
How do we get what?
The homogeneous solution?
Work it out. I'm not going to tell you. You got this, you got this, you got this. You know, y of 0 equals 0. Plug 0 in and see what you get. Y prime of 0 equals 0. Plug 0 in to the derivative and see what you get. Y of 0 equals 0 tells you A is 0. Y prime of 0 equals 0 tells you B equals 0. As I said here. And if you just do it, you'll understand totally. I don't need to tell you that. There are other things I need to tell you, because there are other things that, you know, I got messed up on the solution last time. That's mainly because I hadn't looked at it in a year and something didn't click, okay? Meaning I should have looked at it before class, taking account of the fact that I can't rely on clicks as well as I used to. Okay, everything clicked up to a point, but okay, we'll see where that is. Anyhow, our particular solution, well, if we're combining derivatives of y and multiples of derivatives of y to get a cosine function, then y better be some combination of sines and cosines. So here's our solution. I already crossed out the sign. Why? Because the first, well, the function itself doesn't have a, well, the function itself will have a sine as a result of this, and a cosine as a result of this, right? Second derivative will also have a sine and a cosine, corresponding to the sine here and the cosine here. If I had a first derivative, then I'd have a cosine term related to this sine, right? And a sine term related to this cosine, as you know if you've done some of these. A bunch of them, hopefully. So we see immediately that that goes away, and if you don't understand that, and even if you do, you should plug this in, solve for C1 and C2, you'll find that C2 has to be 0. We did that last time. So, we just eliminate this, okay? And then we run through the rest of the evaluation of the constants. It's very straightforward. You get your particular solution is going to be 1 over omega naught squared minus omega 1 squared cosine omega 1t. Okay? If you don't understand it, just do it. It's just simple. Okay? And if it turns out that you can't do it, then hang your head in shame and holler at me, and we'll see. But I don't think there's a snowball's chance that you won't get it. Okay? Unless you're just in the state of mind I was last time, where you just don't think of something obvious. Okay? And that can happen. And I pretend it happens all the time to me, so you won't feel bad. You still see the process. Okay, well, I'm not always pretending. Seldom am I pretending. Okay. Anyhow, you get this. There's your particular solution, and that's the whole thing, because your homogeneous solution is 0. Solution to the homogeneous equation is 0. Right? Okay? So, how's this function related to the parameters of the problem, to the omega 1 and the omega naught? Well, clearly, if omega 1 approaches omega naught, this denominator approaches infinity, right? So somehow this thing's going to approach infinity. Okay? But it's not really clear how that approach works. And this is the point at which I failed to do the obvious last time. Okay? So what are we going to do? Well, first of all, we're going to let alpha equal the average of omega naught and omega 1. Okay? So it's omega naught plus omega 1 over 2. And that average is pretty much the frequency of this kid's increasing and decreasing oscillations. Okay? Not the frequency with which the envelope changes, but the frequency of each oscillation is going to be somewhere between omega naught and omega 1, and actually for an omega 1 that's close to omega naught, in other words, for a driving frequency that's close to the natural frequency, could be very close to the average. So we're going to use a sum of angles formula, okay, and decompose this into an oscillation, the oscillations at this frequency, and oscillations at frequency beta equals half the difference of these frequencies. Okay? Now you should immediately see in your head, but probably don't, but kind of store it away, and hopefully it'll start occurring to you. Maybe it already had. So it's like we have omega naught here, omega 1 here. So right in the middle, here's alpha, the average of the two. And what's beta? It's how far the average is from either omega naught or omega 1. Okay? So for example, if your angular frequencies were, let's say, 0.7 radians per second, because this swing takes a while, okay? Or, 0.7 nanoseconds if you have a really fast electronic circuit. Because everything we're doing here also applies to electronic circuits, right? mechanical oscillations and LC circuits have identical mathematics and analogous interpretations. And of course, we're developing that in physics, but we're pretty far along with that, so you want to think about it. Okay? Okay, so anyhow, we have this. Okay, here's our alpha and our beta. So if it's 0.7 radians per second, and this is 0.71 radians per second, then alpha would be 0.705 radians per second. Makes perfect intuitive sense that this thing, you know, the kid could be going back and forth with an angular frequency 0.705 radians per second, okay? And that's like about a 9-second period, big long swing. Kids love those. They never get to be on them because they're dangerous. I don't know. Built my daughter one about 60 feet long. She's about 10 years old. And I get back 40 feet. Well, maybe not quite that far. I had a 40-foot running path between where I could grab onto the swing and where I'd push her and where I'd duck out from under it so I didn't get killed. Okay. It was great. It was great. The branch wasn't strong enough to support her in the next year, but she had that for a year. Okay. Wouldn't support my older daughter either. Yeah, she's 4 years old or so. It was great. Loved it. Do that now, they get you for child abuse or something. Well, off the subject. Now, okay. Again, 0.705 radian per second angular frequency, right? Difference in angular frequencies is, that's a 1/100th of a radian per second. Half that's, 5/1000ths of a radian per second, right? So there's your alpha, there's your beta, 0.705 radians per second, 0.005 radians per second. Now, the 0.005 radians per second is a measure of how long it takes this thing to go in and out of phase, right? It's the difference in the angular frequencies, okay? So this beta is going to determine how long it takes to go in and out of phase. The alpha is going to determine how long the individual oscillations take. So you're going to have, and we'll get it in a minute when we do a little bit of manipulation, you're going to have something like this. You're going to have an overall envelope where this distance is dictated by beta. Beta, again, remember, being half the difference between the frequency and the angular frequency. And then within this, you're going to have, of course, we complete this. So within this, you're going to have the individual oscillations. The smaller beta gets, the longer it takes to go through this whole thing. And the more oscillations you'll have within it, because the number of oscillations isn't going to change much. The average is going to be close to, if it's a 0.7 radian per second natural frequency, and omega 1 is close to that, then that's about what it's going to be. It's going to approach 0.7 seconds as a limit, but it's always going to be close if omega 1 is close to omega 0. So this is going to stay about the same, but the envelope is going to extend much further as as omega 1 approaches omega 0. Because as omega 1 approaches omega 0, this is going to approach 0, right? And beta is going to become infinitely long, and you're going to then end up with something at intermediate stage, you would have this with many, many oscillations, okay? In the limit, it's going to approach the, well, bounded by straight lines, okay? Because, you know, locally, the sine function is bounded by straight lines, okay? So if this thing, well, you think about that. Okay, so how are we going to analyze this in terms of alpha and beta? Well, we're just going to note that omega 1 equals, in terms of alpha and beta, how are you going to get omega 1?
In terms of alpha.
In terms of alpha and beta, how would you express omega 1? You've actually got two simultaneous equations here that you could solve for omega 1, but it's obvious how to combine them to get it, especially if you've worked with hyperbolic functions, hyperbolic sine and cosine in your calculus class. If you worked with that in any of your engineering classes, yeah, you're going to see a lot of it. Okay, real important. And it's easy. You know, I saw it in my first year of calculus. What's the big deal about this? Why are we even studying this? Has something to do with a cat in there? Okay. Okay, yeah, I see how that works, but I never come up with it on my own, at least not at 18 years old, my first calculus course, right? And some people could. I mean, you know, I was a real good school, so. Okay, how's omega 1 related to these? Well, it should be obvious that it's alpha minus beta. If you've done the arithmetic of hyperbolic sine and hyperbolic cosine, then this is very much like it. It's like e to the t plus e to the negative t over 2, e to the t minus e to the negative t over 2. How do you combine those? Okay? Anyhow, there it is. Well, cosine of omega 1t is a cosine now of this, which equals what? Well, that should be obvious, okay? Because these formulas for the sine of a sum or the cosine of a sum come up a whole lot. And you really want to nail that now, if you haven't already, okay? Should have been nailed when you took your pre-calculus. So it's time to nail it down.